So we have here the web page for the class. I can see that at the same time. So we can see here we have the web page, and I say that the videos for week 8 are now available. We're now in week 8. And if we go to this link, we can see that there are 3 videos for you to examine. And this week, we're going to be looking at optical communication systems, which is not covered in the textbook that we're using. It's not covered in SCLAR. And so I have given you some other reading, in particular, chapter 4 of this book on fiber optic communication systems, which talks about receivers. And then there is an article on optical amplification. So these are 2 topics that will be covered in the video. And also there's the first one concentrates on noise, so sources of noise. And 2 sources of noise you'll see in the video. There are thermal noises and shot noises, which are covered here. And then there is noise coming from active amplification or erbium-doped fiber amplifiers. And the theory behind how we would simulate the noise for such a system is given in this article. The second lecture for the week is on filtering in optical communication systems, and there is a paper which specifically examines filtering. And then finally, there is information on the simulator that you will be examining in the second series of homework assignments. And so there are 3 videos. The first 2 give you a lot of background and theory, and the last one gives you a hint on how you can work with the homework system. So the reason that we go through this is really to take a deep dive into how you would do a simulation, and a fairly sophisticated simulation of a communication system. So we have to get specific. So to be specific, I chose, in this case, optical communications, because the noise in such systems are difficult, more difficult than might be in a typical simulation. And so this gives you a chance to learn how to take theory and put it into a Matlab simulator, and to go through several validation steps. So one of the most important aspects of working on these optical communication system simulators is that you have to have confidence in your simulation. How do you know that there's not a bug in your Matlab? There's not some error that will put off your research results, for instance. So even if you're using a simulator to examine a situation for which theoretical curves are not accurate, that's why you're going to a simulator, you still need to do a validation. And this is a homework assignment is really about, first of all, how you take theory, put it into MATLAB, and second, how you validate that what you have is accurate. And then afterwards, how you go on and do a Monte Carlo simulation where you get away from theory and you estimate bit error rate by just sending a lot of bits, sending them through a system that you have pretty good confidence in, and then seeing what the bit error rate is when there is no theory. So that's the main idea of this week, the objectives. So you can understand that the first set of objectives is about a particular optical link. So understanding the different kinds of noises. And then most importantly, understanding how to simulate these noises in an optical link. And what makes optical link a bit more difficult is that it has square law detection, which is not a linear receiver because of that square law detection. Now, in the second part, we're looking at filtering effects. And in this case, filtering effects in optical systems. But the general idea of moving to a Monte Carlo simulator is because all of the theory that we have put by so far, all of these equations are only valid when you have more than enough bandwidth for your communications. And when you don't have enough bandwidth, well, then these equations are no longer valid. And what can we do? Well, filtering is something that is well understood in terms of simulation. So we can turn to Matlab to simulate the effects of filtering. And then, again, we can use a Monte Carlo approach where we just send bits, count errors, in order to estimate what the bit error rate would be in these conditions of severe or, in any case, bandwidth limitation. And so there's an article about that. And basically, we're trying to use our simulator to recreate some of these results in this paper. So let me go now to this section on the homework assignment. So I'll go back to the front and we'll go to the homework assignment. And that should be highlighted. The highlight should be down here. So we have new homework B, system simulator for bit error rate. And there are 3 assignments. The first one is due Monday of next week, so before our next in-class meeting. This is a fairly simple part of the homework, so I hope it will not take much time. But you do have to watch the videos in order to be able to complete that. So I gave you the weekend to do this homework assignment. I concentrate on just shot and thermal noise in the first part. And in the second part, which is due Friday of next week, you concentrate on the second noise source. And then I give you another week to actually look at the filtering effects. So in the first 2 sections, we're looking at basically the theoretical curves for this particular optical communication system. And then in the third homework assignment, you're actually looking at the filtering effects with the Monte Carlo. So the 3 different sections require you to, in some cases, complete part of the Matlab code. That's in these first 2. You'll be completing Matlab code. And in the last one, it's more analysis, looking at the difference between theory and Monte Carlo and why the differences occur and what's the utility of doing a Monte Carlo simulation. So I mentioned here, there's the assignment, there are the files, there's some text to help you. In addition to the textbook and the articles that I've added, this is just some of my personal notes about this section this week that we'll be going over. So there are a number of different resources for you to use, different materials for you to use this week than we have typically used in the previous week. So there's not much PowerPoint. And there's no SCLAR section. So you're looking at a different set of sources. So in the case now of the assignment, I would like to, there's a lot of video that's going to give you details of the assignment. And so I don't want to go over that again. You'll have your time to look over it. I will now share with you the actual assignment. So here is a block diagram of the system, which is actually being simulated. And there's, like I said, the videos will take you through step by step with all of these different elements. I'm going to concentrate today on some of the, I'll say a little bit of the mechanics and logistics working with Matlab, and then I'll let you work on the theory behind it, when you have time to look at I can see right now these 2 numbers should have been changed. But in any case, the first homework, we're looking at theoretical values, and theoretical, but no amplified spontaneous emission noise, so only with thermal and shot noise. There's the reading, which is most appropriate for this part of the homework assignment, and the viewing. Of course, you have the lecture and the lecture on the homework assignment. And now we look at the Matlab files, which are provided. And they have the main Matlab file here, homework, that should say B, not B1. I can see I can have a couple of errors to fix on this PDF, but I'll fix them right after class. And by the time you download them, they'll be fine. So there's a main file, which basically calls all the other files. And there's a homework file, which is the theory part. So at some point during this main file, you'll call the theoretical in order to plot curves for the specific parameters that are being simulated. And in particular, there are lines which are now empty in this Matlab code, which you should be able to complete. And you'll be able to complete these by looking at the theory presented and basically transcribing what is the theory, all the equations presented there, into MATLAB commands. So there are a couple other sections of the simulator, and again, you don't need to know how these other ones work, right? You do need to know how the theory part works, but for the rest, it's only if you're interested that it's provided. But basically, we use a couple of filters. We use a Bessel filter, which is actually the filter here, the low-pass electrical filter. We use at one point an RC pulse, so there'll be several pulses, shapes that are being examined with this external modulator, and one of them will be an RC pulse, as we looked at earlier. Another one is a super Gaussian filter, and that is used for this optical bandpass filter. So different elements have different filtering. Filtering is sort of the emphasis of what we're doing, so I highlight that these are the subroutines used for filtering. And then there's the Monte Carlo, where we actually do our error counting, our thresholding. So those are different sections. So all of this is provided in the MATLAB code. What is it you have to turn in? Well, you'll run the file, and in there are several sections. And what you're going to have to do is uncomment the section which is for homework 1. And I'll be taking you through the MATLAB code in a few minutes. Then I want you to turn in a zip file with the name homework B1 and then underscore and then your family name. And you can turn that in via email like we have in the past. And in the zip file, well, we have to have your completed homework theory.m. So I should be able to take what you've turned in, and then when I run it with this code, I should generate the same curves that you're going to be turning in. So you're going to turn in a PDF file also, and in the PDF file, you'll have, well, graphs that were generated by the code, and there's some very nice graphs that are automatically generated. And then you'll also have to put in the information requested below. And what we're asking you to do is to complete a table. So we're looking at two-sided bandwidths, and you'll see when we look at the theory that the performance, the noise is parameterized by the bandwidth of the signal. And of course, we've seen earlier that there are many definitions of bandwidth. And because that we're going to be examining different pulse shaping filters. So the pulse shaping filter could be a non-return to zero, a return to zero, or the raised cosine pulse. And first, one definition of bandwidth would be the main lobe bandwidth. And so I sort of filled that in for you to begin with, supposing that there should be a couple of errors I can see there. That should be 40. But if the bit rate is 20 gigabits per second, then I ask the question, what would be the main lobe bandwidth for a non-return to zero? And if we look at the main lobe of the sync function, it would be 20 gigahertz. If we looked at the return to zero, which would be twice as wide, it would be 40 gigahertz. And if we looked at I'm sorry, these numbers were from previous bit rates, and I forgot to update them, but they'll definitely be done. 50% raised cosine, and of course, if we started from 20, that would be 30 gigahertz. But this is main lobe, which is not a very nuanced bandwidth definition. And so what I ask you to do is, what is the noise equivalent bandwidth? And indeed, it's already calculated for you in the MATLAB file. It's found numerically rather than analytically. And I just want you to make note of here, basically to draw your attention to these characteristics as they are important. And here there's one at 45 gigabits per second, here 20 gigabits per second. So the first thing you'll do is complete this table, and this will help you to answer some of the questions later. Then you'll turn in, as I mentioned, the Matlab code, and remember to complete lines 34 and 35. I give you a hint where to find the theory in the reference about this. And then a couple other lines that have to be filled out also once you get that basic set going. So you can see that there's a shot noise contribution, and that's the SN here in these variable names. And then there is thermal noise. And this should say thermal noise, not shot noise. Should be making all these corrections. Okay, so you'll do it for shot noise, then you'll do it for thermal noise, and then you will combine it into some combined, shot noise plus thermal noise into one total one. So those are the steps that you're going to have to go through. Then you'll see the graphs which will be generated, and I want you to put them in the PDF file, and there'll be 3 curves at 20, one for each one of the pulse shapes. And then we have discussion about the results. And so we're going to be looking at signal and noise powers. And there are a couple aspects I want you to notice in the simulator. For instance, when we plot, these plots are going to put bit error rate versus received power, whereas in the past, we have always used signal to noise ratio. So I want you to notice that this is different. And I want you to discuss how are they different. And why is it easier to use received power experimentally? And so I want you to think about that, why that would be the case. Then I want you to think about what was the method used to normalize the noises in this simulator. And so I ask you a few questions about the thermal and the shot noise. Are they independent of signal power? This is an important concept. And what parameters specifically from the signal are influencing your noise? So what signal parameters influence thermal noise, and what signal parameters influence shot noise? So these are to draw your attention to concepts that I think are important. Finally, you're going to contrast the performance of the 3 pulse shapes. You'll do a validation, and this will be just like the video that I provided. I provide a video that does the validation for 10 gigabits per second. And actually, I just want you to redo this for 10, just as I did in the video. I said 20 here, but the numbers that are provided in the textbook are only applicable to 10 gigabits per second. So you're going to have to do it at 10. So here I'm saying that you're going to be completing this section for 20 and 45 gigabits per second, but you can always change it to 10 gigabits per second. Do your validation at 10, and then if your validation is good at 10, you should be able to have confidence when you change it and do it for 20 and 45 gigabits per second that you've done a good job. And then again, what parameters influence the curves? So some of these curves are going to be similar, some are going to be dissimilar. When they're similar, why? When they're dissimilar, why? Which parameters are making this different? And then the last section, we'll just discuss sending something at a low data rate, sending something at a high data rate. Why are these things different? How are they different? And what would be the advantages and disadvantages of different pulse shapes that you'll be looking at? So that was very quickly. Now I'm going to try and show you what the Matlab code does so that you will be able to understand a little bit more about what you're going to be doing in the homework assignment. So that is the assignment, and now I'm going to take you into the actual code. Okay, so this is the homework theory, which is the one you're going to have to complete. You have here, for instance, these are ways of calculating the current generated by photo detection. And, one of the questions about where's the power influencing it. So you can look at this code to try and figure out, how the current is determined by signal power. And here's a section that's about ASE noise. And in the first section, of course, you won't be looking at ASE noise. Here we have the section where you're looking at shot noise, and here is the section when you're looking at thermal noise. And right now you can see that there's nothing here. I say if we're not looking at shot noise, set it to 0, but when we are looking at shot noise, when the flag is set to 1, then what should we be using for the shot noise? So you're to look at the equations from the lecture, from the textbook, and to look at the parameters that are used in the Matlab code, and to write an equation for the shot noise. And the same thing occurs here for the thermal noise. It should also be used here. And some of the equations are here in the comments to help you along with the names of different constants and variables. Then the last section, of course, you found the signal noise, you found the shot noise, the thermal noise, and now you'll be combining them into one noise on the 1, noise on the 0. You'll see in the lecture that this is different in an optical system. Here is the section on ASE. It's commented out to begin with, but when ASE is active, of course, then you'll want to complete this as well. And this will be for the second homework assignment. So the first homework assignment has you looking at these, and the second one has you looking at ASE. So this would be the theory part. I don't see any questions in the chat, so I'm going to go on at this point to look at the homework assignment. And this is the main routine. And in the beginning, we clear all the variables. So we start clean each time. Here's the lower rate, and this is something that could change. So for instance, for the homework assignment, I specified 20 and 45 gigabits per second, but you could change them here. For instance, you could change it to 10 in order to do your validation so that it would look like what's done in class. Roll-off factor for the RC pulse, and you could play with that, but I think for the homework assignment, I specified 0.5. Now you'll see that at the beginning, there are 3 sections for 3 different homework assignments, and they're all 3 commented out. So if you tried to run this, it wouldn't run because some of the main flags haven't been set. But we'll look at this now. If you wanted to do homework assignment 1, you would come here to homework assignment 1 and you would say uncomment. And now you can see that you have the Monte Carlo flag is set to 0 because there's no Monte Carlo simulation in the first homework assignment. The shot noise, the ASE noise is set to 0 because we're not looking at that noise, but the shot noise and the thermal noise are set to 1 because they are examined. Now, if you're going to run this, it would not run well because when we get down to later, the section that says theory, of course, you haven't filled out those last sections yet, so you're going to get an error message when this comes in. I'm going to put in here now the solution so that I can run this for you because I have it completed. And so it's going to give the right, when I simulate it now, you'll get an idea for how things are going. So I know I'll just mention for the other 2 homework assignments, of course, the flags change just depending on what the assignment is about. So in this case, I'll just briefly, everything is very well commented, but I'll just take you through some of the parts of the bit error rate, the simulator for bit error rate. And by the way, I'll be recording this class and posting it so that if you have questions later, you can refer to it. So I'll be putting this onto the web page and a link also onto the homework assignment. So there are various system parameters. For instance, when you're doing the Monte Carlo simulations, these are the parameters that would apply. It talks about, how many times you would run the Monte Carlo simulations. When you're doing a block of data to look for errors, how large a block would you want? How many errors should you count in order to get good estimations? So this is parameters that I have set for you in some homework assignments, I might have had you play with that, but not this year. A maximum number of bits, that's so that you don't end up simulating for too long a time. I stop at 5. I'm not sure what kind of computer you're going to be running this on. I think you could use the same computers that you used for the VSA. You could run Matlab on there. And so that would be a more powerful computer maybe than what you're having. Putting a 6 in here might give you slightly better results for your Monte Carlo simulations at the end of the run. But if your computer is not that powerful, then maybe it would take a long time. So that's why I put in 5 here. So here we're putting in the bit rate and the pulse shaping options. Since in this homework assignment, I have 2 bit rates. So now that's why this is going from 1 to 2, and I have 3 pulse shapes. It's going there. If for any reason you wanted to concentrate on one or the other, you could change these, but this is the loop that is going to be run. I assume that the gain is selected, that it balances all losses, and so with the normalization, this is like a gain of 1. Next, we look at the amplified spontaneous emission, and what's put in the comments here are basically what's covered in the lecture, but it's the way of finding the power spectral density for the amplified spontaneous emission noise. So in particular, we assume that this noise source has a flat power spectral density and that it is fixed. And then I give you the value that is to be used for this. And bring your attention to the fact that what the units are that are being used. So this is the spectrum for the ASC, so it's the noise level for the additive spontaneous noise. Optical filtering. So I say that we are using a filter. This is all about filtering, and filtering is introduced in a couple of locations. But here is the main limitation on performance, is that we say that our optical filter is only 50 gigahertz wide, and no matter what signal we try to put through, the optical signal is going to be filtered at 50 gigahertz. So that's why something at like 20 gigabits per second, depending on the kind of pulse shaping I use, could be well within that, and that would represent a simulation where the theory should apply. And then when we go to 45 gigabits per second, well, it may or may not be, 50 gigahertz may or may not be sufficient to cover that, depending on the pulse shape I use. So here is the setting for the optical filtering. Extinction ratio is, how close to zero a zero is. So extinction ratio is the power of a 1 divided by the power of 0. We're not examining extinction ratio in this simulator, so I make it like really, really good extinction ratio. So this effect will not be seen. It's also possible to use a numerical threshold instead of a theoretical threshold. And in this case, we're not doing that, but in the Matlab that's provided, there is the option to do that, but we won't be covering it this year in the homework assignment. So the next are a bunch of constants, which are used in the theoretical equations. So I'll leave that there. Here are the 4 loops where we start cycling through all of the different cases that we're examining. So pulse shapes, 3 pulse shapes we're examining, 2 bit rates, a low and a high rate, and then which kind of noises. So if we're only doing shot thermal noise, or if we're doing shot thermal noise and ASC noise, those are like 2 loops. So the noise is also a loop. Now here is where we're sweeping the x-axis. So we're sweeping the received power. And here I say we're going to do 50 points that we're going to be examining from a range of -40 to 0. Now, if you were really simulating a system, you might not know what is the right range to do, and you might have to do a very large range until you find out what the range of interest is for you, but I found that for you. Then we sweep through this minimum to the maximum in these many points, put it in dB. And now we come to some other simulator parameters. For instance, we're doing oversampling of 8 samples per bit. The bit interval is set to be 1 over RB, and the sample interval is the bit interval divided by the number of samples. Here we're doing the Monte Carlo simulation. So how many BER points? Well, we're getting a point for each one of the powers that we're sweeping. We'll do some zero padding on the time window, but you don't need to worry about that. We do Fourier transforms. We go from the time domain to the frequency domain. So here we're calculating the frequencies for the time window that we're going to be examining. Here we're calling on the super Gaussian to set the optical filter. So here's your optical filter, and here is the bandwidth of the optical filter. And then here is the order of the super Gaussian. And the larger it is, the more flat, it's more square it is. And so we have a very high order. So it's going to be very sharp roll off on this optical filter we're using. Here we do our pulse shaping. I put in a fairly large delay for the raised cosine filter, which means that it should be, really accurate as a raised cosine filter. Overcoming the causality. Here we're actually just shaping the pulse depending on which pulse we picked. And then we do some normalization of the shape. And we come up with this HE is the pulse shaping filter, and it's been normalized so that we can do a bandwidth calculation. Here's a very important step in the simulator where we get the noise affected bandwidth. And so if you were to look at this equation and then you look at our theoretical description of the definition of noise equivalent bandwidth for a filter, of course, this would be it. We're basically integrating, this is an integration of the square of the filter response over the entire frequency band. And that because we have already normalized it so that the peak occurs at 1, that gives us the noise effective bandwidth. And again, you could go back and look at it. It was like one of the first lectures of the course about how to calculate noise equivalent bandwidth. There's a little routine here to plot the spectrum if you're interested in looking at the spectrum and seeing the noise effective bandwidth. I just put it there in case you're interested. Now, in this class, we're using a fixed Bessel filter. We're not using a matched filter. This is something that happens often in optical systems, that matched filter could be complex to implement in a very simple system, and so they would go with a fixed Bessel filter. The Bessel filter would have a width, which is adjusted depending on the signal. So if I use 20 gigabit per second or 45 gigabit per second, of course, the received filter should change. And if I use non-return to zero or return to zero, the bandwidth would change. So you can see that this is all parameterized by the effective bandwidth of the signal. So basically, I'm trying to get a Bessel filter, but that is at least the correct bandwidth for the system, for the signal I'm sending, even if it isn't the matched shape to the signal I'm sending. So here we have the a normalization constant. This is important for match filtering. For a fixed Bessel filter, doesn't really affect it much, so I don't even use the normalization constant. But there's a little text provided for anyone who's interested in. If we had this year done match filtering, we might have concentrated more on this. But this year I decided not to concentrate on that. So finally, we get down to the simulation, and this is about the thresholding, whether we use the theoretical threshold or if we try to come up with a numerical optimal. We're not going to be using that because in this case, the threshold the flag will be set to 0. So finally, down in this section, we're basically running the Monte Carlo simulation. So we run the Monte Carlo simulation, and first of all, we we generate the theoretical values, and then we go and we start doing the Monte Carlo values. And of course, if the Monte Carlo is not set, then this will just not run the part where I count errors, and we'll just plot the theoretical. So I'm jumping down here to, this is after all the errors, counting, So that was all Monte Carlo part. So finally we get to the plotting of the results. And this is about normalizing the received power on the x-axis to make sure everything is hunky-dory. And basically the received power is directly determined by the transmit power, because we have normalized everything, assumed that our gain exactly compensated so that whatever was transmitted was received. In a real system, you would have some losses, you would have an amplifier, and the amplifier would have a gain which just equaled the losses. In this system, we have no losses, so the gain is 1. So finally, the last section is about some pretty plots that plot your results. So I'm going to now run the simulator, and I think I have now uncommented it for homework assignment B1. So when I hit run, so this is the window, the figure that is automatically generated, and you can see the titles say which bit rate, first the bit rate, then the pulse shape, then the noise, SH for shot noise, TH for thermal noise, and then the roll-off. And then we also have plotted here is the bandwidth, and this is the noise equivalent bandwidth for these signals. And so that's what you would use to fill in your form, the table in your system. And so in the homework assignment, the video, I take the 10 gigabits per second, and I take the textbook, and I say, well, at 10 gigabits per second, they happen to give me a data point for 10 to the minus 4, and then I can see, you know, is this received power right for that value? So here it's 20, and so I think the textbook doesn't give it for 20. I think it gives it for 10. That's why I would suggest that you could go back, for instance, to the Matlab code, and I could change the lower rate to 10. I could run it again. And now for 10 gigabits per second, I could see where the intersection point is for 10 to the minus 4, and I would try and see if that power is the right power. And of course, I can always resize the window if I need to get something a little more accurate. Now let's go back to the Matlab code, and let's comment out homework assignment 1. And let's say that I was going to look at homework assignment 3. And let's look at the other example. So now I'm going to look at 10 and 40 in this case. And I'm going to run it. And now let me switch back now to, so you can see it doesn't take long to, it should not take long to run these simulations. So here are now the results for the Monte Carlo. So you can see there's both theory and Monte Carlo. You can see that on the top, I have no ASE noise on the first 6. Second one, I have ASC noise. And so, for instance, you can see how things are shifted because I have ASC noise. And you'll see that, you know, when the bandwidth is 80 gigahertz, of course, that's much greater than 50 gigahertz. And that is why my Monte Carlo simulation is going to be different than the theory. And, you know, I welcome you to play with these parameters if you're curious, and not just do the ones for the homework assignment, but this just gives you a chance to play with filtering effects. So again, if I use a 10 gigahertz bandwidth, just like I use in this case, the Monte Carlo and the theoretical fall right on top of each other because the theory is accurate. I'm pretty much not constrained by the 50 gigahertz optical bandwidth. Everything is working pretty much the way I expected. If I go to a system with 80 gigahertz, of course, then I expect that it won't be accurate. And so these are the kinds of things that you'll be looking at.